Hello and welcome back to Physical Geology. Today I want to look at Lab 1, Introduction to Science. And I made some notes, and I know some of you may not have your lab kit yet, but you can still do this lab because I've supplied the lab sheets for you on our Angel course page. Now if we look at the document camera here, we'll see that this Intro to Science lab deals with the scientific method and approaches for solving problems, right, in science. So remember, it's a sequence of steps that systematically analyzes scientific problems. And you make observations, and there's two types. One is a qualitative observation, right? And the qualitative one is like, what's the color, description of the fabric or the texture. And in minerals, we'll talk about this term called luster. And luster is how the mineral reflects light, right? And so you really can't measure those. They're more of an assessment, and it might be different for different people. But the important one are the quantitative observations. And these are the ones where there are numbers that you can measure, you can weigh, you can use rulers to measure length and width. So those, or measure velocities, times, right? Those are the measurable ones, the quantitative ones. Now, remember, we've mentioned a little bit about this, but the lab kind of goes into this idea of this hypothesis and this other idea of a null hypothesis. So the hypothesis, the key thing about hypotheses, and one of the quiz questions I have is that they're testable, right? Testable, and they're a proposed explanation for the geologic phenomena or the observation you're making, and you're going to make an educated guess. Now, the null hypothesis, you can also test that one, but that has no significant difference in observations. In other words, you don't expect to see any differences, and if there are any differences, then it's based on a sampling error, right? So let's look at an example. Your lab has one, but I kind of made a different one here based on seafloor spreading. So when we look at the ocean basins, one of the observations that were really made in the 1940s and 50s, when we were looking at the sea floor, the Navy was doing this, and later that data was declassified in the 1960s. But we found that marine sediment was thicker farther from the ridge axis. So here's the mid-oceanic ridge, and so the ridge is higher above the seafloor because there's actually magma that erupts there, lava that erupts there, so it has a thermal buoyancy. That's why it's higher. But we find that there's very little to no sediment at the ridge axis. But when we go farther away from the ridge, in either direction, we see that the sediment gets thicker. So the hypothesis here is that if seafloor spreading is occurring, then the age of the seafloor must be younger at the ridge and older the farther away you get. Now, in thinking about a null hypothesis, right? So in this case, if seafloor spreading occurs at the ridge axis, then the age of the seafloor should be the same at all points in the ocean basin. So you can actually test that, and if you get seafloor being older at different places, then you have to reject this hypothesis. But it's one way to look at it that way. Now, when we go to this next part here, let's start testing the hypothesis. So we're going to use experiments. These experiments must be replicable, and the key thing about the experiments is they must be systematic and they must be able to be duplicated, right, by somebody else in a different lab, right? And you're only going to test one variable at a time, and we're going to have a control, right, and a control sample. So experiments must use the same exact techniques over multiple trials. And the key thing, if that experiment is replicable, then you can have a valid theory, right? So remember, the theories make predictions, right? And those predictions are testable, and really we're testing them through these hypotheses, right? And experiments. Now there's a difference between the word precise and accurate. So accurate is the exact number. It's what you expect. But you can, let's say the accurate number is 10, but let's say you get 9, 9, 8, 9. Well, these numbers are not accurate because it's not 10. However, these numbers are very precise because you're getting about the same number each time, right? So there's a difference between accuracy and precision, right? So precision is getting the the same values each time you run the experiment, but you may be off the standard, which would be the accurate number, right? So that's the difference between accuracy and precision. Now for variables, so these are the ones that you can measure during the experiment. You can change some, and you really only want to change one, right? In fact, let's look at the two types. There's independent variables and dependent variables. So the independent variable is the one you want to change, right? You want to change conditions of, for example, if you're looking at fish in an aquarium, you want to change the volume of the aquarium, the time of day you're feeding the fish, the sample of food you're giving them or nutrients you're giving them. So these are all variables you can change, right? And the dependent variable are those variables that are going to be affected by these changes. So really they depend on the independent variable, right? So you can think of it as these depending on the value of the independent variable. Now the independent variable is the if part of the hypothesis. If we do this, then what's going to happen? Well, the then part is the dependent variable, right? That's going to be affected by the independent variable. And so when we look at these, in our seafloor spreading hypothesis, if we change the seafloor spreading into not spreading, then the age of the seafloor would be different, right? So that's an idea there. So remember, the independent variables will plot on this x-axis down here, whereas the dependent variable will plot on the y-axis. So here I'm plotting on the x-axis seafloor spreading, right? Some distance from the mid-oceanic ridge, whether it's occurring or not, but we have a distance. And then over here, I have the dependent variable, which would be the age of the seafloor on the y-axis here, right? And so you can see if our idea of our hypothesis, that is, that seafloor spreading is occurring and the seafloor is getting older farther from the ridge, then as we go farther from the ridge, we should see older and older ages, right? So that's what this line is plotting. So there's a line graph here. Whereas if there's no seafloor spreading, the null hypothesis, then we'd expect to see the same age regardless of the distance from the mid-oceanic ridge here, right? So that's one way to view the data there. So obviously when we do go to the seafloor, we do find that the seafloor does get older, not just based on fossils, based on sediment, and really based on this idea called paleomagnetism. We'll talk about the magnetic field of Earth and how it affects, or how it's recorded in these lavas on the seafloor. Now let's look at some controls. So these are data collected in an experiment that is not exposed to the independent variable, right? So there's two types of controls. A negative control, these are data samples in which you expect no change to occur. So in this example, if we are not changing the seafloor spreading independent variable, so we collect basalt lava samples from several mid-oceanic ridges around the world, we'd expect no change because they should all be very young. They should all be 0 down here, right? Because that's at the mid-oceanic ridge. It should all be at 0. However, if we look at a positive control, these are data samples in which we do expect change to occur. In our experiment, if we collect seafloor basalt samples at different distances perpendicular to the ridge axis around the world, we'd expect the seafloor ages to become progressively older farther from the mid-oceanic ridge. And so if we go back to our graph here, at different ages, we would expect the seafloor to be older at different distances from the mid-oceanic ridge. Right? So that's an idea of the positive control. So the next part here discusses unit conversions and scientific notation and significant numbers. So in this part here, all your data must have units, and if there are no units, it's really meaningless. We didn't, because we're measuring things. We're measuring volumes, masses, distances, velocities. So we need to have units on all our numbers. The key to conversions is that we're not changing the value of the number. We're just expressing it in a different way because each conversion is really 1. And so the example I have here, 1 gram over 1,000 milligrams is equal to 1 because 1 gram and 1,000 milligrams are the same thing. So it's 1 divided by 1 basically, right? Because these are the same thing. And so that's a way to think about this. So let's look at this first problem here. And so also page 568 of your book has some metric conversions that we can use. So we know here we want to convert centimeters to kilometers. So usually what I do with these problems, I always say I have something. And so what I have 3,456,000 centimeters. And my goal over here is what I want. And so what I want over here is going to be kilometers, right? And so one way to kind of set up your problem is I need to get rid of the centimeters. So I know that there are 100 centimeters in 1 meter, right? So that's the same thing, right? They're equal. So I'm just multiplying this number by 1. And I know that in 1 kilometer, there are 1,000 meters, right? So the way I set this up is I put the number I want to get rid of, or the unit I want to get rid of, in the denominator, right? And the number that I want in the numerator, right? So here the centimeters cancel out and the meters cancel out. My answer is going to be in kilometers, right? So basically I'm taking this number and I'm dividing it by 1,000 and then by 100, right? And the nice thing about the metric system is I'm just really moving the decimal place over some number of times. In this case, I'm moving it over 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So this is the same thing as saying 34.56 kilometers. So 3,456,000 centimeters is equal to 34.56 kilometers, right? So now let's look at this one here. I have so again I have 32 kilometers, but I want inches over here, right? So I'm gonna have to make a couple of different conversions here. So the first thing, I know that just off the top of my head, I know that 1 inch equals 2.54 centimeters. 2.54 centimeters. So somehow I'm gonna have to include that in there to go from the English unit to the metric unit, right? So the first thing I want to do here, I want to get rid of the kilometers because I want to eventually get kilometers into centimeters, right? So I know that in 1 kilometer there are 1,000 meters, right? And then I know that in 1 meter there's 100 centimeters. And then to get rid of the centimeters, I know there's 2.54 centimeters in 1 inch, right? So by doing this, I'm going to get rid of the kilometers, get rid of the meters, and get rid of the centimeters here, right? And so to do this, I'll just do it on my calculator over here. So we'll take the 32 times 1,000 times 100, and then divided by 2.54. So it gives me a whole lot of inches, right? So we got what, 12,598 42. And we'll move the decimal place over, well, in fact, let's 1, 2, 3. So it's 1,259,842 inches. That's how much 32 kilometers is. We haven't done significant figures on this yet, and in reality, but these we're assuming these are exact numbers, so that's basically what's going to be our inch value there. In fact, you might even want to round this up to 3 there. Now, so that's one way to go from converting from kilometers to inches. So again, it's kind of setting up the problem, and we'll be doing some of these problems as we go along here.